Okay, welcome back to the second part of our lesson on base SI units. We talked last lesson about um, what physics is, how it uses math to describe or predict things in the universe, and we talked about why it's so important to measure things properly. So we're going to see some examples today. I'm going to try to be a little faster. I'm going to break it down a little simpler. I'm going to hopefully make it so easy to understand what physics is that a baby can understand it because I have brought some babies right here. Here I have two babies. They're both great physics students. They're going to help me teach this class. So that's really useful for me. Give me someone to talk to so I sound less crazy. That's always good. So 60 miles an hour is a pretty common speed when we describe speed in real life when we're talking about cars driving. You guys probably don't drive very much, but that's pretty common. It's in miles per hour, which are units that most people have some familiarity with. That's cool. Let's take a quick look. Not here. We'll come back to that. Over here, this problem we did yesterday. A woman runs at a speed of 5 meters per second. I told you it's a speed, but why is it a speed? I could give my speed in like knots if I was sailing a boat. I could give my speed in miles per hour if I was driving a car, but I chose meters per second. Why meters per second? I don't know. Well, time for some very simple physics. Hi there. Hi. If you're going on a trip and it's farther, you're going more distance, will it take you more time or less time? More time. That's right. Yeah, exactly. The farther a distance you go, the more time it takes you to travel that distance. Distance and time are proportional. They're related by a ratio. That's why when we describe a speed, we divide a distance per time. So if we had a unit for distance, like miles, and a unit for time, like hours, we should not make up a new speed measurement like knots or lambs or gubs. We should use what we have in order to keep things simple and make things understandable. And speeds are always in meters per second or a distance per time, miles per hour or meters per second. Either one is fine for now. But since speed is a ratio of some distance to time, that tells you what it is. This is a very big clue that you can use a lot in a lot of physics problems. Look at the answers. 40 meters, 10 meters, 100 meters squared, 200 meters per second. When you talk about a field for like most farmers or ranchers or whatever, they don't care how long the field is. Let's say they have a rectangular field. They don't care how long it is or why it is. They care about how much area it is. They want to see how many plants they can grow or how many animals they can have in that area. If you want to know how many like trees you can grow in a certain field, it doesn't matter how long or wide it is. What matters is how long and wide it is. You've got to multiply them. A field that's 20 meters by 100 meters can grow as many trees as a field that's math is hard. 20 meters by 100 meters is the same as a field that's 1 meter by 2,000 meters. That was a bad example. But yeah, in theory, those fields could grow the same number of trees. So we don't really care about the length or width of a field. If we talk about fields, we're probably going to talk about area. And here, only one of these answers is actually an area because it's in a length times a width, or a length squared, 100 meters squared, or meters times meters. So that's pretty good. We're going to stick with as few units as possible and as simple units as possible for many reasons. If we look at 60 miles per hour, that's okay. But if we're talking about like a teleporter, we could travel super massive distances, not like a mile, maybe like a light year. Light years, light years, light years. If we were living in the future and we could teleport to Alpha Centauri, we would be talking about not miles, even bigger. But if we were talking about the measurements needed by the teleporter to make sure every single atom is in the right place, when you're talking about atoms, you really need very, very small units. You can't use miles. You have to talk about angstroms or microns or super, super small lengths. This is all very complicated. Physicists don't like things that are complicated. They're going to keep it simple. So they're going to use the same unit for all lengths, and the same unit for all masses, and the same unit for all times. Kind of, not really. Let's take a look at something else. This is a really cool little demo. Not this one. That's good to know about, but not really relevant right now. Let's take a look at this. So in physics, we're not going to use miles or angstroms for big and small lengths. We'll use the same thing. We'll use meters. A meter is like a yard, like 3 feet. I'll show you guys an example later. A human is usually about 2 meters. And if you can have a really big sunflower, a little taller, and a gigantic flower called a rafflesia that's a little smaller, they're all around the size of a meter. If you look at giraffes, elephants, and Tyrannosaurus rexes, they're much bigger, but we'll still use meters. These are all less than 1,000 meters. 1,000 meters is a kilometer. It's 0.6 miles. I'll come back to all this stuff. But we can use the same units. A human is 2 meters. A kilometer is 1,000 meters. And we can keep going. There's the Vatican City. It looks like it's about half a kilometer across. There's Central Park. Central Park is it goes from 60th Street to like 110th. It's like 3 miles, so about 5 kilometers, 5,000 meters. Comets, Mount Everest, states, small planets, countries. There's Pluto. We can use the same meters to describe all these lengths. We don't need a new unit every time we get to a new scale. When we're talking about stars, we'll say, oh, it's just a gigameter, or it's just 10 to the 9th meters, it's just a billion meters. Don't need a new unit. So I think you get the idea. It's a pretty cool little simulation. There's a link in my lesson plan, which you can see later. That's basically the idea. We can use the same units to describe everything from the very big and back down to the very small. When we get to things that are smaller than a human, we don't need to make up microns or angstroms. Just say, oh, it's not a meter, it's 1,000th of a meter, a millimeter. Dust mites are on the millimeter scale. Paper is on the millimeter scale, so are amoebas. And we can keep on going down to chloroplasts and mitochondria, the powerhouse of the cell, chromosomes, E. coli. We're still talking about them in terms of meters. They're much, much smaller than a meter. A nanometer is 1/1000th of a meter, and that's about the scale of an atom. But we're still using meters. And we go down super small, we can get back to protons, neutrons, nuclei, quarks, which we'll talk about in June, and the smallest theoretical length in the universe, the Planck length, which is a little bit beyond the scope of this course. But if you talk about string theory, you might learn about the Planck length. Okay. So, for the reasons I've said, we want to keep things simple and be precise all the time. We're going to only use the same units. Miles are terrible. They're the worst. Basically, if you guys use the imperial system, you should know it's very bad. There's like 5,280 feet in a mile, which is just a ridiculous number. we're going to stick with metric, but in science, they're known as the base SI units. And the base SI units are for length, mass, for reasons. Don't say the word weight, W-E-I-G-H-T. We're going to talk about mass. Don't say, oh, I weigh this much, or oh, a whale weighs such and such tons. Things have mass. They have length, they have mass, and we also need to measure time using the base SI units. So forget about feet and miles. They're kind of terrible. We got meters. This is a meter. I can't fit the whole thing on camera. This is a, if I go diagonal, maybe I can just like barely get it. There we go, perfect. 1 meter. 1 meter is a little more than a yard, which is 3 feet. It's 100 centimeters. It's pretty big. So all lengths will use meters or units based on the meter. A centimeter is much more common for small things. A centimeter is about the width of my pinky fingernail, which is kind of small, but most people are pretty familiar with a centimeter. Centimeters also, there's 2.54 centimeters in an inch. Not relevant to you guys, but we're going to use meters. Those are the base unit. This you kind of need to know. It's not like physics, but it's important to know to understand physics a little more. And we'll use them all throughout every lab, all throughout the year. All the problems you ever do in physics will be based on these units. Mass, you guys might think pounds measure mass in imperial units. We're not going to talk about that right now. For mass, the base unit is the kilogram. And a little tiny confusing thing, you might think the gram would make more sense. Kilogram is much more common, which is 1,000 grams. 1 kilogram, so I'll say a meter, is about a yard, a little more than a yard. A kilogram is 2.2 pounds. Another thing, why is LB the symbol for pound? Like, come on, we gotta get on the right page. 2.2 pounds, if you know what that is, it's also the exact mass of 1 liter of water. So if you ever drink a 2-liter bottle of soda, that's exactly 2 kilograms of liquid. Soda doesn't have quite the same mass as water, and you have to think about the mass of the bottle, but that's pretty negligible. A 2-liter bottle of soda would be about 2 kilograms, so about 4.4 pounds. Pretty heavy. And time, very straightforward. You already know, even if you're a baby, these babies know time is measured in seconds. For physics, you should know that a minute is 60 seconds, and an hour is 60 minutes, and a day is 24 hours, but that's kind of common knowledge. I'm not really going to go over that. If you want to know what a second is, you can say Mississippi really fast. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi, 5 Mississippi. That was like 5 seconds. So we got the base SI units. Many units are derived from base SI units. So back to this practice problem. We used physics words. We used meters and seconds in this problem, which was pretty straightforward, which makes sense, definitely. If I was a farmer, I might describe my field in acres, but then I have to remember what acres mean and I have to write something else down, and there's like hectacres and other kinds of weird things that are confusing. I already have a unit for length, so I can just make a unit for area based on length. If I have a 10 meter by 10 meter square field like this problem, or 20 meters by 5, or 1 meter by 100 even, those all have the same area. We all know the formula for area. I'm using formulas that we've all seen before in math class or life. In the future, you'll see physics formulas that are much more explicit in using special physics units. But for now, most of us know that all areas are length times length. So they should have units in length squared or meters squared. And that makes perfect sense. So lots of units are made up of the base units. These are the base units, meter, kilogram, second. Other units are derived. If I want to know the area of a field, I could give it not in meters. You can't say, "Oh, how big is my field? I want to know how many cows I can raise on the field." Oh, it's a 300-meter field. That doesn't make sense. But you could say it's this many square meters. That would be fine. Speed is measured in derived units. Meters per second are a derived unit. Weird example. Let's say you're working in like a water treatment plant and you want to figure out how much water you can provide a city every second or every day, every second. So it's going to be a derived unit. Yeah, we're going to measure how many of a certain amount of how much water we can provide per second. If we wanted to figure out how much per day, we could just do some conversions to change from seconds to days. But to keep it simple, to stick with the base units and make it easier for a physicist, we'll measure per second. Should we do gallons or liters? No, that doesn't make sense. Should we do meters of water? People don't really drink or consume meters of water. How can we describe the amount of water a water treatment plant can produce or treat or whatever supply every second? What do you guys think? I'm pausing here for reasons. Maybe you could say cubic meters per second. Yeah, I don't know. Cubic meters per second, something like that. So yeah, we could say something like that. If I was like really hungry, which I am, and I want to know how much like food I eat, I can measure it in kilograms per second. But if instead I was trying to figure out if I had like some really heavy rope and I wanted to figure out how much my rope weighs compared to someone else's rope, but there were different lengths of rope, I could measure how much mass the ropes had in kilograms per meter. That's a very contrived example, but the base idea, these are base units. We can get derived units from the base units that are useful in a variety of situations. If I want to figure out how heavy my rope is for every certain length, I can figure out how much mass there is per meter. Okay, we talked about SI prefixes. I'll send you guys some stuff about SI prefixes, but obviously meters are not good for everything. That's fine. This is going a lot. All my videos are going pretty long. I was just kidding when I said I was going to make it shorter. It was a joke. I got you guys. But you're AP, so it's fine. Don't worry about it. So if I'm talking about my height, I'll probably talk about meters or centimeters. But if I'm talking about light years and galaxies, I'll be talking about megameters, terameters, gigameters. If I'm talking about mitochondria being the powerhouse of the cell, I'm going to talk about nanometers and micrometers and picometers, really small things. So I'll send this out later. You should know some of the basic ones like centi and milli, but I'm going to write them all down really fast now. The SI prefixes, you just take one and slap it on the unit. So kilo plus meter, kilometer. Pico plus second, picosecond. They are tera, giga, mega, kilo. The the case matters. Uppercase, lowercase. Kilo. What was it? Hecto or hecta or hect. deca. Then no prefix. Deci, centi, milli. This must be a capital T. Micro with a very fancy M. Micro. Nano. And pico. That's enough for now. But they all have a certain meaning. They all mean a power of 10. Tera is 10 to the 12th. Giga is 10 to the 9th. Mega is 10 to the 6th. 10 to the 3rd. 10 squared or 100. 10 to the first power. 10. 10 to the negative 1. 10 to the negative 2. 10 to the negative 3. 10 to the negative 6. 10 to the negative 9. And 10 to the negative 12. So if you see some weird units in a physics problem like nanograms, that just means it's 10 to the negative 9th. I wrote a little too small, but I'll send something out and I'll try harder next time. It's 10 to the negative 9th gram, so it's 1 billionth, not billion, 1 billionth of a gram. Much, much, much less than a single gram. And these are great. You don't have to memorize them. Whenever you take tests, if you were taking tests, you would have a list of these if you needed them. But if you want to remember them, here's a nice mnemonic. T, G, M, K, H, D, D, C, M. This is a mu, I guess, because capital M is taken and lowercase m is taken. They use the Greek M, a mu, for micro. And P, the what do they call it? Mnemonic is thank goodness most kids haven't dropped dead converting many unit numbers properly. So if you want to remember them, there's a little trick. That was all pretty obvious. I want to talk about something really important before we move on. So it's pretty easy to convert. Most people know how to convert them without thinking. Like, of course, I know that 65 centimeters is 0.65 meters, but people mess it up a lot when they go one step beyond. I'm going to show you guys a method that it seems not necessary, but people make this mistake all the time. So I really want to make sure you guys have seen the method. You'll probably come back to it later. You're probably going to think, don't need that. I'm way too smart for this class. I'm the best. And then you'll skip ahead. But then in the future, you're going to see that I was right, because I'm pretty much always right, because I'm actually really smart. So if I want to convert three decimeters to megameters. Well, first write the number you have. 3 decimeters, little d, little m. Okay. Easy question. What happens when you multiply a number by 1? You get the same number. Yeah, good job. 3 decimeters times 1 is 3 decimeters. Not useful. Here's another thing. Let's say I have an equation. Decimeters. I know 1 decimeter, based on my prefixes from before, is 10 to the negative 1 meters. Okay. I'm going to divide this equation, both sides, by 1 decimeter. All right, another easy question. Hey baby, what do you get when you divide a number by itself? Hmm. Hmm. 1. Why did I ask those stupid questions? Take this 1, plug it in here. 3 decimeters times 10 to the negative 1 meters over 1 decimeter. We are going to get the same answer because when you multiply a number by 1, you get the same value. But it's going to have different units. This is really useful. The decimeters on top and decimeters on the bottom